Look at this skeletal diagram of an ethanol molecule. Notice how it spontaneously rearranges into a different structure, ethanol. A single hydrogen atom trades places with a carbon-carbon pi bond, bouncing back and forth between states in a continuous dynamic equilibrium. Chemists call this specific molecular dance keto-enol tautomerism. But in organic chemistry, the real challenge is predicting exactly which molecules can actually perform this swap. This split screen shows our checklist alongside an acetaldehyde molecule. First requirement, it must contain a carbonyl group, like an aldehyde or ketone. Second, find a valid alpha hydrogen. By locating the alpha carbon directly attached to the carbonyl, we see acetaldehyde has 3 alpha hydrogens sitting right there. Identifying these two components looks straightforward on paper, but exams will deliberately test your ability to apply these rules against structural traps. Here is the skeletal structure for formaldehyde. It contains an aldehyde group, passing our first rule. However, notice these hydrogens. They are attached directly to the carbonyl carbon. With no adjacent alpha carbon, there are no alpha hydrogens. Formaldehyde cannot undergo tautomerism. Now look at this cyclic alpha-beta unsaturated ketone. It has a carbonyl and an adjacent alpha carbon with a double bond, but those hydrogens are trapped. Being part of a double bond, that alpha carbon is sp2 hybridized. Rigid geometry prevents them from participating in the swap. We can refine our second rule. A valid alpha hydrogen must be attached to an sp3 hybridized carbon, meaning a carbon surrounded entirely by single sigma bonds. Finding a hydrogen atom isn't enough. It has to be geometrically and chemically available on an sp3 alpha carbon to actually initiate the shift. Let's examine what happens when a molecule has multiple valid locations. This diagram shows an asymmetric ketone called 2-butanone. It contains an sp3 hybridized alpha carbon on the left side and a completely different sp3 alpha carbon on the right side. Pause the video for a moment. Try to draw all the possible enol structures you can create from these two distinct starting points. For asymmetric molecules, tautomerism becomes a structural puzzle where you have to map every valid molecular pathway. This animation shows the first pathway. The pi bond swings to the left alpha carbon, moving a hydrogen to the oxygen to create our first enol structure. If we reset the molecule, we can follow the second pathway. The pi bond swings to the right alpha carbon, yielding a second, completely different enol structure. To save time on exams, you don't need to draw these out. The number of unique structural enol forms exactly matches the types of sp3 alpha hydrogens in your starting molecule. 2 types of alpha hydrogens mean 2 structural enols. This infographic summarizes the predictive framework. 1. Look for an aldehyde or ketone. 2. Locate the alpha carbon. And 3. Ensure it is sp3 hybridized. Notice the equilibrium arrows below the steps. Even though a valid molecule constantly shifts between these two forms, the keto form is almost always the chemically favored stable state. By verifying these 3 specific structural requirements, predicting keto-enol tautomerism is a reliable step-by-step logic puzzle.